So we will continue with Yann Palu's talk on Introduction to Extriangulated. Whenever you're ready.
Yeah, thank you. And so I will begin the talk today with the discussion of an extriangulated category coming from combinatorics. So we start by talking about the combinatorial side of the story. So it's called the non-kissing complex, and it was say mostly introduced by Thomas McConville. So I will quickly recall the link between triangulations and cluster categories. So given a polygon, one can look at its diagonals, and two diagonals may or may not cross. Here there is a crossing. And looking at maximal collections of pairwise non-crossing diagonals, we get triangulations of the polygon. Now, these triangulations enjoy very rich combinatorics, well, due to the existence of flips. So a flip consists in removing one of the diagonals in the triangulation and replacing it with the unique other one that you can throw in to get a new triangulation. So this was categorified by Calderot, Chapoton, and Schiffler by using Verne, Hiroyuki, and Todorov's cluster categories here of type A. And in that setting, the diagonals correspond to indecomposable objects. And the cluster categories have a triangulated structure. That's a result of Keller. And so one can talk about extensions in a cluster category. And here crossings will be categorified by extensions. And thus triangulations will become maximal objects without self-extensions, and those are called cluster tilting objects here, because they categorify the clusters of the cluster algebra of type A. And flips are categorified as a mutation of cluster tilting objects, which also categorifies mutations in the associated cluster algebra. So there are various generalizations of this, for example, to triangulations on any surface, oriented surface. But I want to talk about a different sort of generalization here. And it starts with slightly changing the point of view. So instead of drawing a polygon with diagonals, we write a line divided into small boxes. And the diagonals are now represented as walks inside the line, the grid. But following the rule that says that a walk corresponding to a diagonal should start on the smaller index of the diagonal, and it should start from the top or left part of the grid, and the walk should end in the higher index, either at the bottom or to the right. So I've drawn a few examples here. And you can see that some of the boundary components appear as walks now, but they are straight walks. It just goes straight from one side to the opposite side in a square. Okay, so written that way, diagonals are now called walks, and crossings become a different picture that's called kissing. And so triangulations that are pairwise collections, maximal collections of pairwise non-crossing diagonals become the maximal collections of pairwise non-kissing walks. That's a bit long to say, so they are called non-kissing facets, or simply facets if I'm too lazy. And the flip for triangulations induce a flip for those non-kissing facets. Now, what Thomas McConville proved is that a similar combinatorial flip exists if one starts from a grid of any shape. So here, a grid is going to be a non-empty subset of Z2, but that we draw with boxes instead of dots, so that it's easier to draw walks inside. a walk is going to go from top to, say, from top and left to bottom and right. So Macanville calls them northwest to southeast walks. That's too difficult to pronounce for me, so I will say left top and bottom right walks. So that's an example of a walk. And here that is not a walk because it's at some point coming from left and going up, which is forbidden. You can only go down and right. Okay, so let's, yes, so the notion of crossing for diagonals will now be replaced by a kissing for walks. And a kiss is a local configuration that looks like this one. So here the blue walk omega is kissing the red walk omega prime because they both share a common subpath. But the blue walk is coming from top, leaving to the right, while the red one is coming from the left and leaving towards the bottom. So that's a kiss. And yes, here's an example of a grid where we will list all possible walks in this grid. So first, there are always those straight walks that do not turn, and they should be thought of as the boundary of the polygon for diagonals. And they cannot appear in any kissing. So you cannot kiss nor be kissed by any other walk. So they will appear in any maximal collection of pairwise non-kissing walks. And for that reason, they are often just deleted from the drawings. Now, those are all the walks that turn only once from top to the right. And there's one for each small square. And those, if you, here's the kissing. In a kiss, the blue walk has to turn at least once from top to right, and the red walk has to turn at least once from left towards the bottom. So if all walks only turn from top to right, there cannot be any kissings between those. And so one gets a reduced non-kissing facet. So the word reduced is to remember that we haven't drawn the straight walks. So similarly, all walks that turn only once in the other direction form a reduced non-kissing facet. They are pairwise non-kissing. And there are a few more walks in the grid that turn at least twice. And here's the complete list. So examples of kissings and non-kissings. So on the left hand side, the blue walk is kissing the red one. So there's the local configuration of the kiss here. They're sharing some subpath, and the blue walk comes from top, leaves to the right, while the red walk comes from the left and leaves down. In the middle, it's also a kiss, but the common subpath is reduced to a point. On the right-hand side, however, all three walks meet as in the beginning of a kiss, but the green walk crosses red and blue, so that's not a kiss. And the blue and the red walk, they meet as for a kiss, but then never split off. So it's not a kiss either. Okay. Yes, so a non-kissing facet is a maximal set of pairwise non-kissing walks. And you might be wondering why I'm talking about kissings yet, and why would that be interesting? And in any case. And well, there is a very beautiful theorem by Thomas McConville on maximal non-kissing facets. That's the following one. So first, all non-kissing facets have same cardinality. I would like to point out that this is very far from being obvious. So for triangulations, one can cut along one of the diagonals to reduce the triangulation into two smaller triangulations. And then in order to count the number of diagonals, you can do it by induction. Here, the works are allowed to cross each other. They cannot kiss, but they can cross. And so it's not possible to cut along a work and do some similar induction. So instead, Thomas McConville has to come with some very clever combinatorial ideas. I think it's a very beautiful proof. And using the same idea he has introduced in order to compute the number of works in a non-kissing facet, he shows that there exist flips of these non-kissing facets. So more precisely, if in a facet you choose a work that is not one of the straight works, so a bending work, then you can replace it with a unique other work so as to get a new non-kissing facet. So there is a flip for a non-kissing facet, which is similar to the flip of triangulations. Okay. So when seeing this, one thinks about mutation and cluster algebras. So it would be nice if there is a relation between this and some sort of mutation. So for triangulations, the flip was related to mutation of cluster tilting objects in cluster categories. And our aim now is to find some sort of category that categorifies the flip of non-kissing facets in a similar way as cluster categories categorify cluster triangulations. Okay, so in order, yeah. So here's an example of a flip for a non-kissing facet. So pick one of the works that you want to flip, but before, one has to add in the straight works. They are useful for computing flips. And I've drawn everything so as to minimize the number of crossings. That's important. Now choose one of the works and find the two closest works to that one, So in this example, the meaning of closest is quite clear. But in full generality, this is the heart of Thomas McConville's idea, trying a way to express, yes, to find those two works that should be the closest one to the one you want to flip. So once you've found those two, you can forget about all the others. And those two works in red here cross. So you can resolve the crossing, and the green work you had is part of the resolving. And here's in blue the other part of resolving the crossing. And that's the new work you are looking for. So you should replace the green one by the blue one, and that gives you the flip of the non-kissing facet. So it's slightly more involved than a flip of triangulations, but it's still purely algorithmic. Okay, so we would like to categorify those flips, so we need some category around, and we'll do this by introducing an algebra defined in terms of quivers with relations. So the quiver associated with the grid will have vertices, the squares of the grid. Edges correspond to adjacency. And we want to have arrows, so we decide that all arrows should point to the right and up. That gives a quiver. And now what we would like to have is something like a bijection between indecomposable representations on the one hand and walks on the other hand. But walks are not allowed to go up, right? To turn from left to towards the upper side. So we throw in some relations to prevent this to happen with the representations. So in general, anytime two arrows change direction, we add a relation requiring the composition of those two arrows to vanish. So now we have an algebra associated with a grid, and we want to define walks from representations. So here's a slightly bigger grid. So we can draw the quiver in the grid and then write a representation of the quiver with relation also on the grid. And then what you should first do is erase everything that's zero. So every vertex where the representation is zero dimensional, just erase it. Erase all zero linear maps. Sorry. And only keep the support of your representation. So here's, for example, a representation that's supported on only 3 vertices with 2 non-zero linear maps. And that gives you some parts of a walk. In order to get the full walk, you should, on one side, go one step up and then as far left as possible, while on the other side, go one step right and then as far down as possible. So for those of you that know about gentle algebras, slightly switching point of view, this is adding 2 cohooks to the string of the representation. So there are, yeah. So if the support of the representation is close to the boundary, then going one step up might lead you to the boundary, and then you can't go left. And same thing, one step right here, you've already hit the boundary, so you can stop at that point. So this defines a map sending an indecomposable representation of the quiver with relation associated with the grid to walks in that grid. And the result that was obtained independently by Thomas Brusle, Guillaume Deauville, Pierre Moussavand, Hugh Thomas, and Emine Yildirim, and in collaboration with Vincent Pilot and Pierre-Guy Plamondon, says that this map is injective. So sending a representation to a walk is injective, and you almost obtain all walks that way. So you're first missing all straight walks, which is not a problem because they are somehow irrelevant from the combinatorial point of view. But you're also missing all walks that turn only once from top to the right. There's one such walk for each small square in your grid, so for each vertex in the quiver Q. So in order to get a bijection, we add some symbols pi bracket 1 that should be thought of as shifted projective indecomposables. So that gives a bijection. And this bijection is nice enough to see the kissings. So if omega is the walk associated with an indecomposable representation M, and omega n associated with n, then omega m is kissing omega n if and only if there is a non-zero morphism from m to tau of n. So if you remember from David Stokes, this means that there's a relation between kissing and tau tilting theory. And yes, so the same bijection induces a bijection between the non-kissing facets and basic support tau tilting modules. And in particular, moreover, the flip of non-kissing facets correspond to tau tilting mutation. So that this result is a categorification of the flip of non-kissing facets in terms of mutation of support tau tilting modules. So that's what we wanted to do. But now there is no extriangulated category around yet. So we'll try and see if some appear. So let's look at this example, the same example as before, and draw its AR quiver. So here's the slender right-hand quiver. We can use the bijection to send each vertex to the corresponding hook in the grid. So draw the support and then complete to a hook. And once this is done, we are left with a quiver that's now completely combinatorial. We can temporarily forget about the algebra. And it's now possible to understand the arrows of the AR quiver purely combinatorially also. So if you look at the picture, arrows going up, pointing upward, correspond to sliding the starting point of the hook one step counterclockwise, while the arrows pointing downwards correspond to sliding the end point of the hook one step clockwise on the boundary. So that's this permits to recover the AR quiver quite easily, purely combinatorially, but it also allows us to continue playing that game, right? So for instance, the leftmost hook on the top, if you look at the starting point, it's possible to slide it once counterclockwise along the boundary. And if you do so, you get one of the straight hooks. So let's try and do this everywhere. Keep sliding the endpoints. And that gives a slightly bigger quiver that now contains all hooks corresponding to modules, but also straight hooks and the hooks associated with the shifted projective in the compensables. Okay, so this is not the AR quiver of a module category, but we are going to pretend that it's the AR quiver of an exact category anyway. And we can also hope that this exact category would have extensions corresponding to kissings. And if that were true, then the straight hooks that cannot kiss or be kissed would be projective injective in the exact category. So let's draw this under brackets. And the hooks that turn only once can only kiss or only be kissed, depending on the direction they turn. And so they would correspond to projective or injective objects. Now, as I said, the straight hooks are not relevant combinatorially because they appear in every non-kissing facet. So algebraically, it's quite tempting to delete them or kill those objects. And that would mean killing projective injectives in an exact category. And we have seen on Tuesday that the quotient is now extriangulated. So if we manage to put some exact structure on this abstract category of hooks, we are ending up with an extriangulated category where extensions would categorify kissings of hooks in the group. that's something that I will try to explain now, but I've got to switch device. Um, so, yes. So this example that I've shown, it was inspired from something that was noticed in a collaboration with Yann Palu and Picardie. And the first example was described of such an extriangulated category, described in a collaboration with Yann and Nakaoka. And the general case will probably appear soon on arXiv, and it's in a collaboration with Shagovsky and Hiroyuki Nakaoka. Example there, and the results will appear. So the grid algebras that I've described in the beamer are a specific class, subclass of the class of gentle algebras. And that's the setting in which we like to work. So let me recall a few basics on gentle algebras. To fix an algebraically closed field and consider a basic finite dimensional algebra. And Qi is gentle, it's called gentle, if it satisfies a few conditions. So say in short, locally, it should look like this. Where some of the arrows might not be here and some of the vertices might be identified. And with more details, every vertex in Q should have at most 2 incoming arrows and 2 outgoing arrows. The ideal I should be quadratic, so it's generated by path of length 2. And then for every arrow alpha, there should be at most 1 arrow beta, so there is no relation between alpha and beta, and at most one arrow gamma is the relation. So one composable arrow gamma such that alpha gamma is in I, and one beta such that alpha beta is not in I. And similar condition with the incoming arrows. So for every alpha, there is at most one arrow beta such that beta alpha is not in I, and at most one gamma such that gamma alpha is in I. So gentle algebras are gentle because their representations can easily be described combinatorially using strings and bands. And I'm only going to talk about strings here. So a string is it's a path in Q, but where you're allowed to go in the direction of an arrow or in the opposite direction of the arrow, like that. And there are a few restrictions. So if you just went through an arrow, you cannot take it on the other way, right after, and you cannot go through a relation. So it contains alpha, alpha minus 1 consecutively, or alpha minus 1 alpha, and shouldn't contain alpha beta or alpha minus 1 beta minus 1, where alpha beta is in I. Here's an example. So consider the quiver alpha beta gamma with one relation, alpha beta equals 0. This is a gentle bound quiver. And for example, there's a string that starts at 2, then takes alpha minus 1 to go to 1, then takes gamma to go to 3, and then beta minus 1 up to 2. That's an example of a string. And strings are usually considered unoriented. So this is the same as the string that first follows beta, then gamma minus 1, and then alpha. So those two strings are identified. And then one can associate a representation with a string. So sigma is the string, all right, and sigma for the associated representation. And it's obtained by thinking that the string is describing what happens on some basis vectors. So for instance, the sigma above, there's one basis vector at vertex 2 here. There's one at vertex 1 that is sent to this one via alpha. and the same element is sent to one at vertex 3 via gamma, while a new element at vertex 2 is sent to this one via beta. That gives the representation K, K2, K, identity here, 1, 0, and 0, 1. A result due to Butler and Ringel says that all representations can be described that way, so that I'm only stating a very specific case on the result. So let A be a finite dimensional general algebra that is of finite representation type. Then sending a string to the associated representation is a bijection between strings Qi and indecomposable representations over Qi to isomorphism. And general algebras that are not of finite representation type, one has to add in some more combinatorial objects called bands. There's a vast literature on general algebras, so it's difficult to cite everyone that should be cited, but I picked a few references. So using this string combinatorics and the bijection above, one can compute a lot of things for the representation theory of the general algebras. So it's possible to compute morphisms explicitly just by looking at strings. It's also possible to describe the irreducible maps and thus compute tau and tau inverse. A number of the people have worked on computing extensions and higher extensions in general algebras. And there has been quite a lot of work on derived categories of general algebra. Quite a lot is known now about, on their derived categories also. In order to relate general algebras to the combinatorics of the non-kissing complex, we need to introduce the blossoming of general algebra, and it's starting from a gentle bound quiver Qi. It adds some blossoming adds some vertices and arrows to get a slightly bigger quiver with relation to blossom I blossom, and it's defined. Well, I will show how it works on an example. So here's a gentle bound quiver, and its blossoming is obtained by adding vertices and arrows so that the vertices 1, 2, and 3 of Q are now 4 valence. That's the maximum possible valency in a gentle bound quiver. adding a number of arrows that are necessary for this. But we still want to obtain a gentle quiver, so the direction of the arrows are determined by @2 incoming arrows, @2 outgoing arrows, and there should be relations so that the gentle conditions are satisfied. Yeah. So this example comes from a grid, and it's easier to see on the grid why this makes sense. So here is the gentle bound quiver associated with the grid. And what you're doing with by adding those vertices here, blossoming vertices, is taking account the boundary of the grid. So here, if you add vertices for the boundary components and use the same rule for the quiver with relation, what you get is precisely the blossoming that I've drawn on the right. Yeah. So this new quiver with relation is completely determined by the fact that it's gentle, that it contains Q and I, and that it satisfies the ruling condition. So every vertex in Q is now 4-valent. While every new vertex is a leaf, either a sink or a soul. And here's the relation to Macambier's combinatorics. So we define a hook on Qi to be a maximal string for its blossoming. Let's see that it makes sense on the example. So here's a hook on the grid. This walk goes through, once we've drawn the blossoming quiver on the grid, the walks go through some arrows and inverse arrows, and that gives a string for the blossoming bound quiver. And this string starts from a blossom and ends in a blossom, so it's maximal, or it has maximal length. And yeah, I will stop here for today and explain tomorrow how to get the extriangulated category of works from this construction. Thank you.
Here or Zoom.
Oh, sorry, Ilke, I cannot hear you.
Oh, no?
Oh, yes.
Okay. Now, is this better? Do you hear me?
Yes.
Okay. I hope everybody else also can hear me. Are there any questions or comments for Yann? Over Zoom, just feel free to unmute yourself or type in the chat. Doesn't seem to be the case, so let's thank Yann again. We will resume in 15 minutes at 4:05 UK time.